All right, welcome to this explainer, everyone. Today, we're kicking off our brand new Data Structures and Algorithms series. And listen, if you're a complete beginner, you are in the exact right place. We're going to break down these concepts without any of the intimidating jargon or crazy assumptions. We're just using simple logic. We are starting off with episode 1, arrays. Why? Well, because arrays are the absolute foundation that pretty much every other data structure is built right on top of. Once this clicks for you, everything else is going to become so much easier. So let's dive right in. Imagine you've got 100 boxes scattered randomly all over your room. It is total chaos. Every single time you need one specific box, you have to search through the entire pile, one by one. Super frustrating, right? But now, imagine those exact same 100 boxes neatly numbered and lined up in a single, perfectly straight row. Instantly, you know exactly where to look. That right there is the entire idea behind an array. We're basically taking total chaos and turning it into a perfectly predictable linear structure. Section 1. The big idea here, think of an array as a train. This analogy perfectly illustrates the core structure of an array. Picture these perfectly connected compartments. Each compartment holds exactly one passenger. Let's just call them passengers A, B, C, D, E, and F. They're all joined together in one continuous line, and most importantly, every single compartment has a specific number label right on the outside. But you really need to notice how those numbers are assigned. The absolutely crucial point is this number right here, 0. The numbering of our compartments always starts at 0, not 1. In computer science, we call this zero-based indexing. For whatever reason, programmers just love to start counting from 0. It's a classic hurdle that trips up a ton of beginners. So just lock this into your memory right now. Your very first piece of data sits in index 0. Section 2. What exactly is an array? Okay, so here is the formal textbook definition. An array is a fixed-size, ordered collection of elements of the same type, stored in contiguous memory. Now, I know that sounds like a bunch of dense technical jargon just mashed together, but don't sweat it. We're going to break down exactly what these words actually mean, because understanding these specific traits is the real secret to mastering how arrays work. So, there are 3 key traits you need to remember here. First is fixed size. This just means the array's length is set right up front when you create it, and it doesn't magically change on its own. If you build a train with 6 compartments, it has 6 compartments. Done. Second is ordered. Elements have a strictly defined position, first, second, third, and so on. And finally, the third trait, contiguous. Honestly, this is the most important word here. It means every single element sits right next to the previous one in the computer's memory. Absolutely 0 gaps. Let's look at why that matters so much. Section 3. Let's take a look inside the computer's memory. Because there are absolutely no gaps between the elements, the computer never actually has to search for your data. Instead, it uses this brilliantly simple mathematical formula to instantly calculate exactly where your data lives. It starts with the base address, which is just where the array begins. Then it adds the index multiplied by the size of the data. And the result? An instant jump straight to the exact location. Let's put some real numbers to this to see how cool it is. Imagine we have an array with the values 5, 12, 8, 21, and 3. Let's say this array starts at memory address 100, and each number takes up 4 bytes of space. If we want to find the value sitting at index 2, the computer just does the quick math. 100 plus 2 times 4. That equals 108. It completely bypasses searching and jumps straight to memory address 108, where it instantly finds the number 8. Literally no searching required. This right here is why arrays are so incredibly fast. Moving on to operation 1, access. Because of that clever little mathematical formula we just looked at, accessing data is what we call an O of 1 operation in Big O notation. O of 1 just means constant time. It means it takes the exact same amount of speed and effort to access an element whether your array has 5 items or 5 million items. The computer simply does one tiny math problem and makes a direct jump straight to the memory address. Boom, instant. Operation 2, traversal. Traversal simply means visiting every single element one by one. If we have our array of 5, 12, 8, 21, and 3, and we need to read all of them, we have to take a step for each and every one. We call this O of n, or linear time. The n literally just stands for the number of elements. So if there are n elements, it takes n steps. It scales in a straight line. If the array is twice as big, it takes twice as much time to traverse it. Operation 3, insertion. Now, insertion is a tale of 2 very different scenarios. If you're just inserting a new value, like the number 9, At the very end of the array, it is super fast. It just drops straight into the next free contiguous slot. That's a quick O of 1 operation. But what if you try to insert the number 99 at index 1 right smack in the middle? Well, that is costly. Because memory has to remain contiguous, you can't just shove it in there. You have to physically shift the 12, the 8, and the 21 one step to the right just to make room. Inserting anywhere other than the very end forces a massive shift of everything after it, making it a slow O of n operation.
Operation 4. Deletion.
If we delete that value 99 from index 1, it suddenly leaves this glaring hole in our perfectly contiguous memory block. And remember our golden rule. Arrays cannot have gaps. So to close that gap, every single element after that hole, the 12, the 8, the 21, the 3, must be individually shifted one step to the left. In the absolute worst case scenario, you're shifting the entire array, which is exactly why deletion in the middle is also a costly O of n operation. Section recap, the ultimate trade-off. All right, here is your ultimate cheat sheet summarizing all these operations at a glance. Accessing an element by its index, blazing fast, O of 1. Inserting at the very end, also fast, O of 1. But if you need to traverse the whole list, or if you need to insert or delete elements right in the middle, you get hit with O of n linear time because of all that heavy, awkward shifting. Basically, arrays are incredibly fast to read, but they can be painfully slow to change in the middle. Which leaves us with a pretty massive question. If arrays give us instant access, but really costly, painful inserts when we want to modify the data, is there a different data structure out there that actually flips this trade-off? Like, is there something that makes inserting data completely instant, even if it has to sacrifice that quick array access? Well, the answer is absolutely yes, and that is exactly what we're going to explore next time. Up next in episode 2, we are going to unpack linked lists, a totally different structure that completely rethinks how memory is connected to solve this exact problem. Thank you so much for joining me for this explainer on arrays, and I really can't wait to see you in the next one. Keep exploring!